Hello everybody. In this video, we're going to learn about points and vectors. In particular, before we start talking about three-dimensional mathematics with x, y, and z, we're going to start with two-dimensional mathematics, or 2D for short. That means all the points and vectors that we're going to learn about have two components, an x and a y value. Well, to begin, here's something which is probably kind of familiar, a point. A point refers to a specific location in space, and we give it some coordinates to determine where it is with respect to an xy axis. When writing points, we'll typically use capital letters, like P or Q, and we'll use parentheses to enclose the coordinates of the point. And when we graph them, we usually draw them as dots. So for example, in this diagram, here are 2 points. Here's the point 1, 2, which means you go over 1 unit on the x-axis and up by 2 units. And then over here is the point Q, the location 5, 3, which means you go over 5 units on the x-axis, 1, 2, 3, 4, 5, and up 3 units along the direction of the y-axis, 1, 2, 3. So those are points. You've probably seen them in an algebra class before. Now, something new might be vectors. Now, vectors and points are very similar. They're both going to use 2 numbers, but they represent very different things. In particular, a vector refers to a displacement. That is, a change in coordinates, a change in their values. And to write vectors, we usually use lowercase letters with a little arrow on top, and we enclose the components with angle brackets. So for example, here's the notation to write a vector named v, a lowercase v with an arrow on top. This is the vector 2, 1, and we use angle brackets around that. And displacement means that we go over 2 units and up 1 unit from the starting point. Now, it's really important to keep in mind the location of a vector does not matter. Right? A vector can start at any point you wish. It just means starting from that point, you'll move over in one direction along x and move in a direction along y. And of course, you can move in both positive and negative directions. Here's a vector w. This is the vector -3, 0, which means from the starting point, move along the negative x-axis by 3 units, and move 0 units along the y direction. So this is a horizontal vector pointing towards the left. In each of these we draw as an arrow, which points in the direction that we're moving from the starting point to the ending point. Those points have slightly more formal names. The point you start at is called the initial point, or sometimes that's called the tail of the vector. The point you end up at is sometimes called the terminal point, or the head of the vector. And the amount of distance you travel, or the length of the vector, that's sometimes called the magnitude. And here's an example of a vector u with 2 negative components, the vector -1, -4. Which indicates that from the initial point, you'll travel -1 unit in the x direction and -1, 2, 3, 4 units along the y direction. So those are some vectors for you. Now, we'll often be working with lots of different vectors, and we might run out of letters pretty quickly. There's only so many times you can use x and y without it becoming a little bit confusing. So what we'll often do is say if we have a point P, we might refer to the components as P1, P2. So I'm using subscripts here, right, for the numbers of the components. So P1 is the x part and P2 is the y part. Similarly for Q, I might use lowercase q1 and lowercase q2. Or if I have a vector v, I could represent that as v1, v2. And w could represent that as w1, w2. If there's really only one point or one vector, we might still use x and y sometimes. But we'll more often see this particular notation. Right. What can we do with vectors? Right? We know that they represent displacement. Well, we can calculate the length of a vector, the total distance traveled, using the Pythagorean theorem. As a quick recap, the Pythagorean theorem says that if you have a right triangle with sides of length A and B, and the hypotenuse, which is the side opposite the right angle, with hypotenuse C, there's a formula which relates the sides of this triangle. A squared plus B squared equals C squared. And that's true for any right triangle. Now, how does this help us figure out the length of a vector? Well, let's take a look at that vector from the previous slide. This is the vector v, 2, 1, 2, 1, which means that we move 2 units along the x direction and 1 unit along the y direction. So, if we actually draw in lines showing the displacement in each direction, what we have is a right triangle. And the length of the vector is the hypotenuse of that triangle. So to calculate the length of this vector, the components take the places of A and B in this formula. To solve for C, the length of the vector, we could take the square root of both sides of this equation. So to find the length of the vector, it's going to be the square root of A squared plus B squared, which in this case is 4 plus 1, which is the square root of 5. And for notation, it takes a while to write out the word length, so mathematicians typically use a double bar notation to indicate the length of a vector. And this formula still works even if you have negative numbers. Right? Here's an example of a vector w, the vector negative 3, 0. If you want to find the length of the vector w, it's going to be the square root of negative 3 squared plus 0 squared. Right? Even though this isn't really a triangle, the formula, the algebra, still works. And you'll find that this is the square root of 9, which is equal to 3, right? Which might be the answer you expected. So that's something we can do with vectors. Now, what if you're given 2 points and you want to find the vector between them? Right? If you want to get from point P, with coordinates P1, P2, to the point Q, with coordinates Q1 and Q2, well, to find the vector between these 2 points, that vector v is the point Q minus the point P. In other words, it's the vector Q1 minus P1, comma, Q2 minus P2. So we'll do a couple of examples to maybe get some intuition for why this works. So for example, let's say we have the point 2, 3 and the point 5, 7. To figure out how to get from 2, 3 to the point 5, 7, we calculate the displacement. That vector v is 5 minus 2, which is 3, comma, 7 minus 3, which is 4. And that's how we calculate that vector. And sure enough, if you start at the point 2, 3, and you travel along the vector 3, 4, right, starting at the point 2, 3, if you add 3 to 2, you get 5. And if you add 4 to 3, you get 7. Right? So that's the vector between those 2 points. Now the order does make a difference. This vector brings you from P to Q. If you wanted the vector from Q to P, you just do the subtraction in the opposite order. As another example, here's another point. Let's say P is the point 4, 1. It's your initial point, and you want the vector with terminal point 2, 6. Right? To calculate the vector from 4, 1 to 2, 6, well, again, you take your terminal point, 2, 6, minus 4, 1. Right? So we have 2 minus 4, which gives us negative 2, and 6 minus 1, which gives us 5. So this is the displacement which brings us from the point P to the point Q. Right? If we start at 4, 1, and we add these values, adding a -2 to 4 brings us to 2. Adding a 5 to 1 brings us to 6. So this vector brings us from the point P to the point Q. And that's how you can calculate vectors between points in general. Now, if you want to find the distance between 2 points, long ago in an algebra class, you might have learned something called the distance formula. But since we're talking about vectors, we're going to think of this in a slightly different way. The distance between 2 points, you can calculate that from what we already know. It's the length of the vector between them. Right, so let's take a look at that example we just did. We figured out the vector from 2, 3 to 5, 7. Right, we calculated that using subtraction. We found that was the vector 3, 4. So if we want to get the length of this vector, well, again, we can use the length formula. And the length of the vector 3, 4, that works out very nicely. The square root of 9 plus 16, that's the square root of 25, which is 5. Right, so the length of this vector is 5, which means the distance between these 2 points is 5. Right, so that gives us a way to calculate the distance between points. Let's do one more example. What if we want the distance between the point 4, 1 and the point 2, 6? Well, we calculate the vector between them using subtraction, and we found earlier that that vector was -2, 5. So the distance between these points is the length of this vector. So to calculate the length of this vector, it's the square root of -2 squared, which is 4, plus 5 squared, which is 25. So that'll be the square root of 29. And I guess if you really wanted to, you could do some decimal approximation. It'll be 5 point something. But in general, you can also just leave these as square roots. You never really need to simplify in this course. And if we leave these points in kind of general algebraic terms, you can also learn where the distance formula comes from. So in general, let's say you have a point P1, P2, and then you have another point Q1, Q2, and let's assume you want to find the distance between those in terms of the variables instead of using numbers. Well, following the same process we just learned about, you would first find the vector between those 2 points. So that vector v would be, since it's from P to Q, it would be Q1 minus P1, comma, Q2 minus P2. And then to find the distance, that's the length of that vector, which is the square root of Q1 minus P1 squared plus Q2 minus P2 squared. And that's where the distance formula comes from. Now, what else can we do with vectors? Well, a lot. Another thing you can calculate is the length. Oh, no, we did the length. Another thing we can calculate is the slope of a vector. So to find the slope of a vector, and this only works in 2 dimensions as well. 3 dimensions is a little bit different, but in 2 dimensions, the slope of a vector is really the same thing as the slope of a line. Right? Do you remember in algebra class when you learned the equation of a line? It was y equals mx plus b, and m was the slope. Right? Calculating the slope is a very similar process. And there's many notations we can use. So here's 3. You might see these in different classes. Right? Here, we often like to write vectors as v1 comma v2. But maybe, and if you were taking a physics class, you might see this vector written as delta x and delta y. The triangle is the Greek letter delta. It often represents the change in something. So this notation could also be read as the change in x and change in y, which is exactly what a vector is. But again, in an earlier algebra class, you might have heard these quantities referred to as the run and the rise. Right? Given a starting point and an ending point, right, you move some distance in the x direction, some change in x, that's the run. And then you move up along the y-axis, that's a change in y, or the rise. And so the slope of this vector could be calculated as v2 over v1, or if you prefer, delta y over delta x, or if you prefer, the rise over the run. And so it's just, we're calculating a fraction here. So for example, some of our vectors from the previous slide, the slope of the vector 3, 4, that would be 4/3. The slope of the vector -2, 5, that would be -5/2. So that's one way to kind of figure out the slope of a vector. And we'll talk a lot about this in the next lesson as well, when we actually calculate these angles. But that's coming up next time. Finally, we're going to do some operations on vectors. Just like you can add and subtract and multiply and divide regular numbers, there are some operations on vectors which are going to turn out to be really useful. There's two big ones, and the first one we'll talk about in this video is called vector addition. So vector addition says that given two vectors, let's say we have the vector v, which is v1 comma v2, and the vector w, which is w1, w2, the sum of those vectors, which we'll write as vector v plus vector w, is equal to the vector you get just by adding the components together. So v1 plus w1, comma, v2 plus w2. And that's it. So, for example, if you have the vector 1, 3, you want to add the vector 5, 2, well, you add the first components together, the 1 and the 5, and 1 plus 5 gives you 6. Then you add the second components together. So 3 plus 2 gives you 5. So the sum of the vectors 1, 3 and 5, 2 is the vector 6, 5. Now, part of the reason we care about vector addition is it's got a good geometric interpretation. What this means visually speaking is that starting at some point, we're applying the displacement of one vector and then the displacement of the other vector. So for example, if I start at this point down here, and then I add the vector 1, 3, I'll end up at this point, and then add the vector 5, 2, I'll end up at this point. Alternatively, I could add the vectors first, I'll get the vector 6, 5, and then if I apply the vector 6, 5 to this starting point, it will bring me to the same ending point. Right, so again, in general, if you have a vector v plus a vector w, right, that's kind of like a two-part displacement, you can add the vectors together to give you a single vector, which does the entire displacement with a single vector. If you have the same starting point, you'll end up at the same point. Now, because addition is commutative, it doesn't matter what order you add numbers in, regular addition is commutative means that vector addition is commutative. In other words, v plus w is the same thing as w plus v. So for example, we just calculated the vector 1, 3 plus the vector 5, 2, and we got 6, 5. We would get the exact same result if we took the vector 5, 2 plus the vector 1, 3. Right? 5 plus 1 is 6, and 2 plus 3 is 5. And this observation actually leads to an interesting visual result, which is sometimes called the parallelogram rule. And here's the idea. Now remember, when you're drawing a vector, the starting point doesn't matter. Right? Vectors aren't tied to a particular location in space. So in this diagram right here, here's the vector v, but I could also draw the vector v over here. I could draw the vector v with any starting point you want. So imagine I have the origin, and I draw the vector v, so its initial point is the origin. And that brings us to a new point P. And then from the point P, we add the vector w, and that brings us to a point R. Right? That's the same thing as v plus w. Now, what if I started at the origin and instead add the vector w first, and then add the vector v. So starting at the origin, add the vector w. That brings us to a different point, q. And then if I add the vector v, well, since addition is commutative, I have to end up at the same point, r. And if I draw all these vectors at once, I know that this side and this side, the vector v has the same slope no matter where you draw it. And I know that the vector w has the same slope no matter where you draw it. So I know I have a four-sided figure where opposite sides are parallel. And from geometry, we have a name for this kind of shape. It's a parallelogram. And that's the parallelogram rule. So, just in words, what the parallelogram rule says that if the vectors v and w are positioned with their initial point at the origin O, then the terminal points of P, Q, and P plus Q, which we call the points in this diagram P, Q, and R, P, Q, R, along with the origin O, form a parallelogram. That's pretty neat. Now, there's lots of other operations we can do with vectors as well. In the next video, we'll talk about another operation called scalar multiplication, which is also very important and has a good geometric application. But for now, that's the introduction to two-dimensional vectors. You might also want to start thinking, how would this generalize to three-dimensional vectors? Because that'll be coming up soon as well. But that's it for this video. Thanks for watching.